Okay. Hi, everyone. My name is John Speed Meyers. It's a pleasure to welcome you today to a presentation by James Petersen called Secure the Stack. It's a hands-on workshop, so it should be fun. I'm the Vice President of R&D at Edera. I oversee product management and research at Edera and do a little bit of both myself. I've also been the product manager for EderaON, which James will be using today. It's a pleasure to introduce today's presenter, James Petersen. He is the founding engineer at Edera. To use SoCal language for a Silicon Valley idea, he's an Edera OG. He helped build the fundamentals of Edera and has been essential to EderaON as the first technical lead for the project. And for the past 6 months, Edera has also been lucky to have James serve as a sales engineer. In prior professional roles, James has worked as an engineer at ChainGuard and Anchor. He knows a thing or two about containers, Kubernetes, engineering, and security. So with that, it's our pleasure and my pleasure to have James present today. So over to you, James.
All right. Thanks, John Speed. I appreciate the the intro. So I guess just first some basic housekeeping. We have a channel here or a thread here, so feel free to drop any Q&A. We'll be happy to answer live during the webinar. But yeah, before we get started, especially if you're here or watching this at home, go ahead and go visit on.edera.dev, which is where EderaON, all of the documentation, the license, everything is hosted. So go ahead and sign up. That'll give you one free node of Edera, and that's what we'll be using today. So yeah, go ahead and follow the instructions. This webinar, we have access to some temporary hosts for folks to play around with who are on the webinar. But if you're at home following this after the fact, yeah, please go ahead and follow the instructions on the website, which should help you spin up an EC2 instance or some ephemeral instance and then get Edera installed and everything like that. So first, wanted to start off with just some basic discussion around what is the actual problem that Edera is solving. So the typically what maybe folks realize or don't realize, maybe folks agree with me, that containers are not a security boundary. So containers are actually just kernel structures. The kernel doesn't know what a container is because containers are just namespaces and cgroups. So namespaces basically just segment what a process can see, because ultimately a container is just a process running on a host. And namespaces, like a PID namespace makes the process think that it is PID1, when in reality it isn't. And there are other things like network namespaces to kind of segment network resources, mount namespaces, segment mounts, user, IPC, UTS, etc. And really what these do is they make a nice organizational structure for a process. So that process can, operate as if it's the only thing running. It doesn't have to worry about collisions. I mean, you use namespaces in programming language to also do the same thing. You don't have to worry about collisions because your methods are namespaced and things like that. Cgroups, they are a way to control what a process has access to as far as like CPU, memory, things like that. They're short for control groups. So this actually, if you're thinking of Kubernetes or something like that, where you specify, I want my process to have this much memory, and I want my process to have this much CPU. Cgroups is how that is actually controlled. So it is just a way of controlling resources, but it still has to do that in a single shared kernel. So, these processes, let's say you have 100 containers on a single host, All of those are just processes on a shared kernel. They're namespaces, they're cgroups for each process, but they are still talking to the same kernel. So, like I mentioned, container is really just a UX abstraction. The kernel doesn't know what a container is. It doesn't have a concept of a container, really. It's just a wrapper around some kernel constructs to make operating a process nice, distributing a process nice, things like that. So, excuse me, the idea is that a shared kernel is actually a larger blast radius than you might consider. So let's say you have multiple tenants, multiple containers, you're running a web server, you're running a database, things like that. They all land on the same node. Or you're running two separate customer accounts. Like maybe you're running customer A or customer B, and they land on the same node. They're ultimately sharing the resources of that node. They're sharing the physical resources, but they're also sharing the kernel if they're just running in containers. The kernel is a very large surface. There's a lot of code in it. There's a lot of legacy code in it. There's modern code in it. But ultimately, it is where your blast radius exists. And so one tenant gets breached, all tenants are breached. If there's a container escape in one, you've escaped out to the host, the shared kernel, and now you have access to all other tenants on that kernel. So you can see here just a depiction of that. One gets compromised, the shared kernel gets compromised, and now you have access to all tenants. So this is a little more dangerous with multi-tenancy, and we'll see later Kubernetes isn't designed for multi-tenancy because it just runs containers. So some things that we actually see in the space, folks may have heard of some of these vulnerabilities, but here are some container escape vulnerabilities where containers are just kernel constructs, so you can abuse them, you can escape out to the host. One interesting one that I like to talk about is leaky vessels, where runc, the low-level container runtime, actually left a file descriptor open, and so a container could just say, oh, I want to change directories to this file descriptor that's on the host, it's in the C group. And now all of a sudden you've escaped out to the host and you can, move laterally on that host, take a look at other processes, look at proc, things like that. There are also like the NVIDIA Toolkit, the NVIDIA Escape CVE is where NVIDIA actually, their container toolkit relies on container hooks, and those run in the container runtime to configure things like devices and things like that. NVIDIA being GPU provider needs to configure GPU devices. So tenants were able to actually abuse the container hooks to escape out to the host. So there's this whole plethora of CVEs that have been discovered in the past relating to container escapes, where the whole idea is you can escape out to the shared kernel and then you've compromised the whole host. So it's an entire class of vulnerability attack vector that is abused. And especially in the day of AI, AI is becoming more aggressively used to discover things like vulnerabilities, and it's becoming the whole Project Glasswing and Mythos. The whole idea there is it can actually start to chain vulnerabilities, and so the ability to find a nation state level exploit is no longer millions of dollars, teams of nation state hackers that are discovering and using these building these vulnerabilities, but now it's just an API call to an LLM and you have what you need. So some of the vulnerabilities that were found this year that actually I believe Mythos found them, or folks found them with AI. They're all in these particular vulnerabilities are all in the Linux kernel. So we talked about some container escape vulnerabilities before, which is this class of if I can just escape out to the kernel from my container runtime, then I can abuse the shared kernel. But just wanted to highlight, like, the kernel itself is also an attack vector. The kernel itself also has vulnerabilities in it. I said before, I think I showed, there are millions of lines of code in the Linux kernel. So something like CopyFail actually abuses the kernel's crypto system. And it can be, the crypto system is called by pretty much any application who wants to, talk over HTTPS, which is pretty much everything. And so, it's a perfectly normal thing to do to say, hey, I need this piece of data encrypted. And so you can do that from a container. Most containers would do that. And you can abuse this vulnerability to basically overwrite certain binaries in the host or in the kernel in a very reliable way. So you can just, from a container, not even abusing the container system, but abusing the Linux kernel itself, you can escape out and get root access to the host. And then again, because you're in a shared kernel, you have broken out and you have compromised every other tenant on that host. And actually, I should say, the guidance from Microsoft is basically if you have some malicious actor in a container, consider the entire host breached, and so recycle the node, things like that. So it just reinforces this idea of you escape out to the shared kernel, and now it's the entire node. So taking a step back, how can Edera help? What does Edera actually do? What is our goal? So Edera provides a secure execution environment for software. So what we do is we actually take the idea of a shared kernel and improve it. And you'll see how in a couple slides, but a couple use cases for why you might want to do this would be multi-tenant Kubernetes. Like I said before, Kubernetes is not multi-tenant. It just runs, the idea is it is an orchestrator. It runs containers on hosts, and it is very good at that. It self-heals. It's elastic. It expands up and down. But the actual multi-tenancy primitives don't really exist. It's mostly meant for things like internal applications, single application, external facing sort of thing. The isolation right now is kind of namespace isolation, which is really just isolation by metadata. So, you group things. Again, we get back to namespaces. They're segmenting resources on the node, but also in Kubernetes, they're just a way of grouping resources on the host, or grouping resources in the cluster. And you can do things like write RBAC policy and things around that. So folks who have access to Kubernetes, get blocked, but two different namespaces have pods which run containers which might land on the same host. So you still have this underlying potential attack vector of the node itself, some sort of container escape or vulnerability in the Linux kernel. You have untrusted code execution, which there are kind of I consider there to be two categories of this. One being non-deterministic code from things like AI agents. In order to do their job, they need to generate code and be able to freely execute. And this is a huge kind of unknown in the industry right now, is like, how do we handle these things? How do we put a box around these things? How do we securely let a robot operate for us? I think I've seen the levels of automation for AI is actually tied to the levels of automation for autonomous vehicles, which is where I was actually in that space very early on. But the level of autonomy for an autonomous vehicle, it kind of maps perfectly to AI because autonomous vehicles can be pretty dangerous. And so you have these different levels of autonomy where there's a human in the loop, there's somewhat of a human in the loop, all the way up to there's no human in the loop. Same thing with AI agents. And how do we enable that no human in the loop when we can't see what this agent is going to do? And then there's also what we like to call remote code execution as a service. So think of it like a managed Jupyter notebook, or a cloud platform or something where I am giving someone compute and access to my compute, and the value is they have access to data and compute and can basically just, the only thing they have to worry about is writing their code. This is great. It's a good business model. It allows people to speed up development, but it also has this problem of how do you actually put a box around the people who are coming in? Because you could have malicious actors who come in, install a crypto miner, or come in and they can run any code, they can execute anything, so they try to break out or things like that. So it can be an interesting space. And then I talked about this a little bit with the non-deterministic code, but AI agent sandboxing. So this is a larger topic as of late on exactly what I was saying. How do you put a box around AI agents to allow them to operate autonomously without having to monitor them and have a human in the loop to approve potentially dangerous actions, and instead just put a security boundary around it and let it do its thing with the comfortability that it is not going to break out and do things. So how do we service all of these all at the same time, while in order to provide this secure execution environment for software to enable all of these? Well, we use microVMs. So we talked a lot about the shared kernel early on, and the shared kernel, containers, Kubernetes, excellent ecosystem. It does what it is designed to do. You can distribute your software easily. You can orchestrate it so that it expands elastically. It self heals and things like that. But containers are kind of missing this security boundary, if you will. So micro VMs are when you say virtual machine, everyone thinks like, oh, VMware, or some slow machine that's emulating everything, and I can't get any good performance out of it. It has a lot of extra bloat, and that's mostly true. But the idea of a micro VM is that it removes all of the bloat. It does only what it is designed to do, and it doesn't load anything else. It's super fast. Startup time is comparable to regular containers, but it breaks you out of the shared kernel. So each workload actually now, each pod in Kubernetes terms, now runs its own kernel. And so what that does is now things like container escapes or kernel vulnerabilities, yes, they can still affect that workload, but it only affects that workload. So it doesn't affect anything else on the host itself because you have put everything into this sandbox. You've isolated it all. So, like I said, shared kernel is the problem. That's the problem that microVMs are trying to solve, that Edera is trying to solve, that containers have, where the shared Linux kernel actually is your attack surface. But then you use microVMs, and each tenant gets their own kernel, like I said. So the guest kernel is now your attack surface. And that attack surface, a breach of one of these tenants is only a breach of that one tenant. And the nice thing about Edera is we actually run containers inside our microVMs. And so the microVM is a completely stripped down Linux kernel. So it boots only what it needs. And that boot is very, very fast. I think it's on the regular Docker is 300 milliseconds to launch the process. And Edera's microVMs are 400 to 500 milliseconds or something like that. I'll have to look at the latest numbers. So it's comparable to actually starting a container, but you're booting a Linux kernel, and then that launches an Edera init process that launches our container runtime every time you want a container inside a pod. So for us, one microVM maps to one pod. So you still run containers inside of there. You have namespaces, you have cgroups. You can do things like Docker and Docker inside of a tenant, which is a natural reason to run a privileged container, which is dangerous on a shared host, on a shared kernel, because you now have a privileged process that is doing things. It's actually talking directly to the kernel. It's easier to escape out of. But with a microVM, you can run something like Docker and Docker in privilege mode, and it's talking to the guest kernel. It's not talking to the shared kernel that everyone else is using. It's only talking to its kernel. So any sort of escape or abuse only affects that microVM itself. So just reiterating a lot of what I've already said, microVMs, the idea is that you build for breach. You assume that your workloads are going to have malicious users in them, and you just handle that by the design of the system. There's no, alerting after the fact or network policy to try and, assume that this node has been breached and try to control what it has access to and things like that. You just assume this workload is compromised. Let's put all workloads in a box, assume that they can be compromised, and you can still have things like security monitoring and like network policy, things like that. But the runtime layer is taken care of. So you have a strong foundation that you start to build off of. And it actually provides this security model that you can start to trust versus basically having nodes that you need to be able to plan out at node outages or node restarts anytime you have someone getting into your system. Instead, you've shrunk that down to workload level. So yeah, the blast radius, like I said, shrinks from the node to the workload. So putting these side by side, you have tenants on a shared kernel. If one is malicious, you've compromised every single thing on that host. With microVMs, with Edera, if one tenant is malicious, you have just compromised that tenant. Everything else on the node is untouched. This is interesting for security reasons, but also, say, for reliability reasons. If you have, like I was saying, recycling nodes could cause downtime, could cause problems. But also, let's say you have 8 GPUs attached to a node and they're all sharing a kernel driver, and there's some panic in that kernel driver or some GPU causes an issue. All workloads on that node go down who are trying to use those GPUs because it's a single point of failure. And instead, what you can do with microVMs is you can attach one GPU per microVM. They each have their own kernel driver. And so you can increase the reliability, because if one goes down by accident or maliciously, the others are still up and running. So Edera is not the only thing out there right now. There are a couple other microVM providers, if you will. So there's Firecracker, which is AWS's tool that they use for like Lambda and Fargate and things like that. And it's a great tool. I would recommend folks to go look at it. The idea is it starts fast. But yeah, there's some plugins with Kubernetes, I believe, but it's not quite as meant for that environment. There's Cloud Hypervisor, which is more meant. It's a CLI for interacting with KVM and creating VMs. So you can create full VMs. You can also create micro VMs. So we just came out with a KVM based backend, and we use Cloud Hypervisor to create micro VMs. So you can build, it's kind of a Lego kit, plug and play, build things yourself. Kata containers is meant for OCI runtime. So it's mostly built for Kubernetes, where you run a KVM based virtual machine for pods. So similar idea to Edera, and they're KVM only. So it does require some things like nested virtualization or hardware extensions. So you either need bare metal or, like I said, nested virtualization. So it can make expanding on just standard EC2 instances kind of difficult. And then there's Edera, which the whole idea is we're making this space easier. So with multi-tenant Kubernetes, making that possible by providing a secure execution environment for software. So like I said, multi-tenant, AI agent, things like that. We are giving you the product that puts a box around those things. One nice thing about Edera is we actually have a para-virtualized backend, as well as a hardware extension backend like KVM and Zen. But the running para-virtualized actually allows us to run on standard EC2 instances. And that's because we don't require hardware extensions. So if you want to use that elasticity of a public cloud, it can be a really nice thing to still put a box around whatever you're trying to do, but allow you to expand and contract on regular instances. Like I was mentioning, startup time comparable. The performance that we get out of this, out of our architecture, is actually near native. So we actually see that we're closer to just standard Docker than we are to the other virtualization platforms out there. But it is commercial. The other three are open source, free to use. We're a commercial product. We have some OSS components, like we've open sourced our container runtime and some of our OCI libraries and things like that. But the core, like microVM technology, is commercial. So along with that, you get all the commercial goodness of support and get to talk to me if you run into any issues. So, all right, workshop time. So, like I mentioned earlier at the very beginning with the housekeeping, if you have not signed into EderaON, on.edera.dev, please go do that. Sign into on.edera.dev and create a license, and then we should be ready to get started. So I'll give folks a minute to do that, and then we'll come back. So hopefully folks have had time to go sign up for EderaON. I am going to share my terminal. So on the EderaON docs, you should create a key, and then you can go to what is EderaON, read a little bit more about it, especially if you're doing this after the fact. I highly encourage you to read through all these docs before you get started. There's step 2, prepare your VM. So for folks working on this at home who are watching this recording, you'll want to follow that step to create an instance that you can throw away at the end. That's my preferred method, so that you can play around with things and not have to worry about any leftover state or anything like that. Edera runs on Linux right now. We have support for macOS coming here pretty soon. So you'll want a Linux machine. And if you're installing like our Zen backend, the thing that does pair virtualization, it does things like mutate the boot and things like that. It installs a hypervisor. So that's the only reason we recommend starting off with an instance that you can throw away, just so you can kind of get used to things, and you can always go and spin up a new instance, and you get a single access to a single node at any given time with EderaON. So if you throw away an old instance and want to spin up a new one, just go back to the UI and click deactivate machine, and then you can activate a new machine. So it makes it nice and easy. So let me go ahead and share. All right. Hopefully everyone can see this. So in step 3 of the on.edera.dev documentation is install Edera. We have this nice helper script that should allow you to just run and it'll install Edera and it'll do everything that you need. There's also a tab called Option 2 Manual, which is where you can go run through the manual install process. So things like Docker login and Docker run. But yeah, feel free to use this script. I'm going to go ahead and run this. So this is installing the Zen backend, my personal favorite backend, because it's the most performant. And there are some interesting features or properties of using something like Zen, which is a type 1 hypervisor, versus KVM, which is a type 2 hypervisor. And I'm happy to get into those. Maybe we'll get into those in a later webinar. But type 1 gives you strong isolation even between the host and the tenants. Type 2 is still a virtual machine manager running on a shared kernel. So it gives you that strong isolation between tenants, but they are still, if you are somehow able to escape a virtual machine, then you can break out to the shared kernel. So there are some interesting properties. Probably in a future webinar, we will compare and contrast those. So we are rebooting our system now, and the reason why is because we're installing a type 1 hypervisor, and that type 1 hypervisor, we need to boot into that so that it can boot our Linux kernel for the host, and then run all the Edera daemons. So we'll give it a little moment to reboot. Wait for these nodes to come back. I'm doing this live, so hopefully folks can see that it takes a little time to reboot, but everything is normal. All right, there we are. All right. So we should have Edera installed. It's that easy. If you're still on step 3, you can run these instructions, just copy down below. So you see we booted into Edera's Linux kernel. Let's see if Zen is here, because we used our Zen backend. There we go. And the Edera daemon. Oh, ignore this. This is just because I'm using a GCP instance. But you see we're active. So Edera is, like I mentioned, it's basically a micro VM orchestration platform. You can operate it just through an RPC interface. We have a public RPC interface. You can operate it through our clients. I just want root privileges to talk to the Edera daemon. But you can see here, Edera is installed. We're able to see some information about the host itself. If you want to, HV console, you can see the console of the actual hypervisor itself. So you can see what it's doing with hardware, some of the virtualization options, things like that. But what does Edera do? How do we make use of it? So typical container would be Docker run or something like that. So how do we actually do a Docker run equivalent in Edera using the Edera client? We have some work coming out soon that should allow you to actually plug into Docker. And so Docker run with an Edera backend should create a micro VM and run the container inside of it and things like that. But what we're talking about today is actually just interacting with Edera directly. So the Edera client, and then we'll get into some Kubernetes things. So how do we do something like Docker run hello world? Well, Edera has this concept of zones and workloads. Zones are the micro VMs. So zones are what actually create this virtual machine. You can create it, manage its resources, look at its console, things like that. Workloads are containers, and workloads run inside of zones. So the process for launching a container is create a zone, launch a container inside of it. So let's do that. Test. This is probably my license, just because I did not. It's always a license. So let's do this. Yeah, it's okay. I am going to take a look at my license, so I'm going to stop sharing for a brief moment. All right. That fixed it. And this is actually an excellent example of some friction that folks might see. You should be able to go to, I believe, our FAQ to fix this. But this is, I had a node activated from an old instance that I was playing around with before this webinar and just forgot to go deactivate it. So when I authenticated and activated my daemon, it said, hey, you already have a node claimed. So all I had to do was go to, oh, sorry for my screen there. All you had to do was go to on.edera.dev and click deactivate node, and then restart the restart the daemon, and it activates this machine. So going back to what I was saying, Edera has this concept of zones, which are microVMs, and workloads, which are containers that run inside the microVM. So what we want to do is launch S. Let's actually protect zone list. And so you see here, we have a virtual machine. And it's ready to go. It's launched. So how about we protect workload launch hello dash zone. So we want to launch this container called hello in the test microVM. And so there we go. It launched that workload. We launched a hello world container. It says hello from Docker and everything. So we launched that same container that we Docker ran in this microVM. And there you go. It's that easy. So what are some interesting things that we can do with this? There's great documentation on Edera, the EderaON website. So if you're following along at home after the fact, please feel free to run through all of that. There's, standard client interactions. So launching a zone, what can you do with a zone, launching a workload, things like that. And then there's interacting with Kubernetes, which is potentially the more interesting thing. But just a couple fun things I'd love to point out. Actually, you know what? Alias p equals because I am lazy. Let's see. So we can destroy this. We have no more. So there's a bunch of different things that you can actually do with these microVMs. Basic instructions for launching them, destroying them, things like that. There is nothing inside of them. So it might be a little bit confusing at first, where you say, oh, I launched a VM. I should be able to SSH to it, or you see maybe an exec command here. I can exec into it. But the reality is it's a micro VM, so it has nothing in it. It literally boots the Linux kernel and a single binary that we've written. So there's no busy box, there's no shell, there's no distro or anything inside of there. That's how it can boot so quickly. So typically, if you're trying to protect zone exec bash or something like that, you'll get a failure because there's nothing in the zone in the micro VM to execute. So what you'll want to do typically is run a workload, so you can actually get like an Alpine shell. So test, I can do that. Workload launch dash in Alpine in the test zone, and then latest, something like this. So I've launched a workload, and you can see it here. So Alpine sh. And so now you can see I'm actually in my Alpine container inside the zone. So I can do things like that. You can launch a privileged container and do things inside the micro VM. One interesting case, which I think we'll get into in a future webinar, is Docker and Docker and how that interoperates with CI, so things like Actions Runner Controller and things like that, and actually running a privileged container and running the Docker daemon inside a micro VM. So you can do all of your normal Docker operations inside a container, but you don't have to worry about breaking out to the host or anything. What else? So another interesting thing about these is you can update the resources. So resources for this VM are not static. They can be. You can specify static resources, but you can also have dynamic resources. So it balloons up and down with the memory and CPU that it is actually using in the moment. So you can have tighter bin packing. You don't have to define everything up front. There's also a notion of kernel events. So now we have this kernel per workload, and what that means that we can do things like scrape/proc and get useful information that would normally be related to the entire host, but now it's related to a single process. So you see here kernel events. So feel free to play around with that. Kubernetes, though, let's quickly, I know we're getting close to time. I apologize, John Speed, I'm taking up all the time. So with Kubernetes, you can launch a pod with just basic pod spec. To launch it in Edera, all you need to do is a runtime class. Should really set this alias up for all my machines. Runtime class. So you see here, I've pre-installed the Edera runtime class. There are instructions on how to install it in the EderaON website. But let's go ahead and I'll just steal this from the EderaON website. So, like I mentioned, this is the only thing that's required to run an Alpine container or to run a pod. So let's go ahead and destroy this zone so there's nothing left. Yep. And then we can apply pod.yaml. And you see it's already running. So you see here, we destroyed the test zone. And now we actually have Kubernetes interacted with our CRI, created a pod, and inside that, or when it created that pod, what it created was a zone and it created a zone and a workload. So now everything that you can do with the client, I would encourage people to start off with the client, but now everything that you can do with the client, you can actually do through Kubernetes. We have some good documentation on how you do that. But yeah, in future sessions, we'll get it more into using this with like agent sandboxing Kubernetes or Docker and Docker, or a couple of different use cases that actually make use of Kubernetes itself. But for this one, I would encourage folks to, familiarize yourself with the Edera client and interacting with Edera primitives and things like that. And then we'll get to higher level things in the next one. And John Speed, let me go ahead and go back to the slides. And yeah, do you want to talk through EderaON or this slide?
I'll just mention you've seen James using EderaON. The docs are at on.edera.dev. There is a private Discord channel. Check it out. Come join. You can ask questions, run into bugs. There's also a GitHub repository where you can put in bugs or make feature requests or talk about frictions. I was just going to ask a quick question, James, before we run out of time here in 2 minutes. I'd be curious for your take on how Edera fits in with AI, especially AI agents.
Yeah, it's a really good question. So, like I mentioned before, AI sandboxing is a big topic right now. So, Edera provides that secure execution environment, which maps pretty nicely to sandboxing, but you can actually get a couple interesting things out of this, out of Edera that you can't necessarily get out of just your typical sandbox. So, it provides a sandbox, but we also do things like integrate with Spiffy Spire, so you can get workload identity you can get an identity, cryptographic identity for the zone, the microVM that is coming from the hypervisor itself. And then you can also get an identity for a workload running inside of that zone. So you can start to have very strong identity tied to your workloads, and you can start to do some interesting things like MTLS or attesting that an agent workload running inside of a zone is the actual agent, and that it's what you want, or things like tool calls, agents calling tools, and they can call down and make sure that that tool is the thing that they want to be running. So you get some interesting things on top of just the sandboxing. But yeah, it provides that runtime layer for AI agents, and especially if you want to run that on your own infrastructure in your own environment.
Cool. Thank you so much, James. Well, again,
Yeah,
it's been a pleasure to have everyone attend today. And James, thank you so much for your excellent presentation and workshop.
yeah, absolutely. Thanks, everyone.